So we've got differentiation. Which is the branch of calculus that we're focusing on right now. There's the other one is integration, which we'll be doing later. Now, differentiation by first principle is defined to be the limit as h approaches 0 of f of x plus h minus f of x over h, which you can alternatively interpret as the limit as delta y over delta x as delta x approaches 0, which is then written as dy dx. So remember, what this means is that it represents a rate of change, ultimately. Ultimately, it's a rate of change. If you want to be more specific, then it's an instantaneous rate of change of y. If you want to be even more specific, it's the instantaneous rate of change of y as small changes are made in x. Now, that is the definition above. But of course, when we started with that, we did limits, and we could definitely work out the answers, but we found that that took quite a bit of long time. So for things that, you know, are very kind of commonly, things that we come across commonly, then we'll kind of do shortcuts. So we recognize that if we're trying to derive x power n, then that'll be nx to n minus 1. And that's really the key one you know for the moment. Then you've got general rules, like if you're trying to derive k times a function, then it's equal just times k. You can take out the constant times the derivative of that function. If you're trying to derive a sum of functions, then it's just the sum of the derivatives. And similarly for the differences. And then we have our rules on top. You guys mentioned the chain rule. Were there any other rules that we went through, Paris?
The product rule.
Yep. Now we haven't gone through the third rule, but can you guess what the third rule is going to be, Janelle?
It was called the quotient rule.
Yeah. Now, I don't believe we've gone through a quotient rule yet, but remember, these rules always apply whenever you're doing any sort of differentiation. So as long as you're differentiating, you need to think about if you need to use these rules. And there is an additional trigger. So the trigger for a chain rule is, Paris, when do you have to use the chain rule?
When you have something to the power of something.
No, I mean, that's probably what, you know, as I mentioned before, people think the chain rule is about powers, but it's not really. It's not very obvious to you right now because all you know right now is how to derive powers. But Janelle, what's the chain rule about?
Functions.
Yeah, what about functions? More specific.
Of a function.
Yeah, so they're about functions of a function. Or in other words, you're deriving a compound function, right? So you're deriving, for example, g of f of x. So if you're trying to derive g of f of x, that's a compound function. It's got g, then f. I know right now, and for some time, you'll probably associate it with powers because all you know is how to derive powers, but it's not just powers, right? Product rule, Paris, what's the product rule about? When you derive a
function.
Not just any function, like you need to derive a function times a function. That's when you use the product rule.
Right.
And the quotient rule, as you can probably guess from the name, Janelle?
You divide things?
Right, it's a function divided by a function. We'll go through those in a moment. But just continue revising from what we did before. You've got ddx of x to the n equals nx to the n minus 1. We also gave you a sort of more comprehensive version, the ax plus b to the power of n version, which you can choose to memorize if you like. But alternatively, you can just think of this as a function, ax plus b, of a function, or a function, power n, of a function, ax plus b. So that means you derive this function first, so it's n, ax plus b to the power of n minus 1. Then you need to multiply by the derivative of the inside, which is your a. So you can either treat this rule as a separate rule to remember, or really it's just applying the chain rule to this using that rule. Does that make sense?
Yeah.
All right, so let's quickly revise the chain rule. There was a little bit of confusion, I think, about that. So the chain rule is when is your trigger? It is when you are deriving a function of a function. So, as we mentioned before, you guys preferred the notation of y and u. So that means dy dx equals dy du times du dx, where, of course, y is a function of u and u is a function of x. So, example, if y equals, x squared plus 3 to the power of 7, then we can think of this as u. So we can think of it as y equals u to the power of 7. And then we can think of u as equaling x squared plus 3. You can choose to do it separately if you like. Dy du means you're deriving u to the power of 7 with respect to u, which is 7 u to the power of 6. Du dx must equal derivative of x squared plus 3 with respect to x, which is 2x, which means your dy dx is dy du times du dx, which you can think of as 7 u to the power of 6 times 2x, which you can then think of as 14x times x squared plus 3 to the power of 6. Does that all make sense?
Yes.
Yeah.
Yeah. Tiffany? All good as well?
Yes.
Did you have any trouble with the homework, Tiffany?
No.
All right. So product rule. Now, you guys preferred UV for this last time. So remember, the trigger for this is when you are deriving a function times a function. In other words, a product of functions. Note, it's a product of functions, not constants. If it's a constant, you don't need to worry about the product rule. Just treat it like a constant, as we did before. So because a function times a function is a product of functions, that's why it's got a product rule. So that means if we're trying to derive u times v, then we're saying it's u v dash. Well, often it's quoted the other way, I suppose. Doesn't really matter. Really, all it's saying is if you're deriving a function which is a product of two functions, then derive one, multiply by the other, derive the other, multiply by the first. Add the things together, right? So, as an example, let's say I wanted to derive 2x plus 3 against, x squared minus 4. Now, of course, we could expand and then derive that way, and we can do that. But if we didn't want to, we could potentially treat this as u, treat this as v. So you might write out u equals 2x plus 3, and that means du dx is 2. You might write out b equals x squared minus 4. So that means dv dx is 2x. And then applying the product rule, you would then say dy dx is, well, u, which is 2x plus 3, times 2x, which is your dv dx, or b dash, and then swap them around, plus 2 times x squared minus 4. Yeah, and then you can do your sort of, then you can basically expand and so forth if you like. Just and then you're done. All right. Any questions with that so far?
No.
All right. Now we will get onto the quotient rule very shortly, but because you guys are familiar with these two rules for the moment, I just want to make the questions a little harder. So note, the rules always apply when the condition is met. Doesn't matter when that is, but as long as the condition is met, use the rule. So, for example, all right, let's say I wanted to derive this. All right, I want to derive x squared plus 3 to the power 7 times 4x squared minus 3. What do you guys think? How do we do this? How would I derive this?
You use the product rule.
Right. You will probably just go, hey, that looks like it's this times this. So we'll just use the product rule, right?
Mm-hmm.
So this is a product, hence product rule. So you might go, okay, let's say u equals x squared plus 3 to the power 7. And we might say v equals 4x squared minus 3. All right. So the product rule needs me to work out what u dash is. So Tiffany, what's u dash?
7 in front. And then bracket x squared plus 3 to the power of 6.
Yep. Everyone happy with that? Tiffany's happy with it. Janelle, Paris, are you both happy with it?
Do you have to use the chain rule?
That's exactly what I'm getting at, right? So this is u, and you need to derive this. But this is a function of a function. So here, in working this out, chain rule is triggered. So you bring the 7 down. So just treat it like a new question, right? You bring the 7 down, you've got x squared plus 3, but you need to multiply by the derivative of that. So yes, you do need to use the chain rule here. So what I'm really getting at when I say that, the rule always applies when the conditions are met is don't think that, oh, I'm just using the product rule, so that's it, I'm finished. You know what I mean? I'm just complicating it slightly here where, you use the product rule here, that means you need to derive this thing and it needs to derive this thing. And now this thing's pretty straightforward, right? Hopefully. So hopefully you'll see that dv must equal just 8x, right? But when you derive the one on the left, what you need to actually do is you need to use the chain rule. Let me just call it v dash to keep it consistent. So, and you note that for every rule, including the one we haven't gone through yet, for every rule, the chain rule, you need to take a derivative. The chain rule involves you taking a derivative. The product rule involves you taking 2 derivatives. So, and the quotient rule will involve you taking derivative as well. So in other words, whenever you apply one of those three rules, you're going to need to take a derivative again. And that derivative, you just need to treat like a new question. If that needs you to use the rules again, twice, 3 times, 4 times, then so be it. It's like if you get something wrapped up many, many, many times in the post. If it's wrapped up 10 times, you just got to undo it 10 times, right? Doesn't matter, you know, if you've already done 5, if there's another 5 to go, you just keep going. So now you've got u dash, now you've got v dash. Then putting it together, you would then say the derivative of x squared plus 3 to the power of 7 times 4x squared would equal basically 14x x squared plus 3 to the power of 6 times 4x squared minus 3 plus 8x times x squared plus 3 to the power of 7. And we don't really need to expand that. Just as a tip, especially when you use product rule, a lot of the time you don't need to expand and look more for factorization. So you can see x squared plus 3 to the power of 6 here. You've got x squared plus 3 to the power of 7. So take out power 6. You've got x here and x here. And 8 and 14 both have 2x going to that. That leaves you with 7. 4x squared plus minus 3 plus 4, x squared plus 3, which is then much easier to simplify. Does that make sense?
Yeah, that does.
Yeah. So just make sure whenever that you are doing these questions with differentiation, don't think that you've applied one rule and that's it. Always examine what you're differentiating and think about, do I need to use the chain rule? Am I taking a derivative of a function of a function? Do I need to use the product rule? And I'm taking the derivative of a function times a function. Am I deriving a quotient of functions, a function divided by a function? In which case, we would need to use the quotient rule, which is the last one that we need to now go through. So as has been hinted from the name, the trigger for this one is when you are deriving a function divided by a function. Hence, quotient of functions. Now we could actually derive what the quotient rule is, because if you've got something like y equals u over v, where u and v are functions, then one way we could also do it is to, like, sort of as an extension, you could prove the quotient rule using the product rule by considering y equals u over v is the same as u times 1 over v. And then by applying the product rule to that, you will hopefully get the quotient rule. Okay. Now that's not necessary though. You can do that as an exercise. But if y equals u over v, then the quotient rule tells us that y dash, or dy dx, must equal. Now, first thing, many students forget this. There's an over v squared, all right? A lot of students jump straight into the numerator and then forget there's a denominator, like there's a fraction. So don't forget that 1 over v squared. Now the numerator will look very similar to your product rule, but it's not the same. And unlike the product rule, you do need to pay attention to the order. You need to pay attention to the order because while it is like the product rule, where you've got one derived times the other, and then derive the other one times the other one, so you swap around. The reason why order matters is that it's not plus, but it's minus. Product rule, we don't care. It's plus, doesn't matter which one you do first. Quotient rule, it matters. So remember, you must derive the numerator first, u dash, times the denominator, minus derive the denominator times the numerator. And that is your quotient rule. Does that all make sense?
Yes.
All right. So what that means then is when we're doing the quotient rule, if we take an example and we say, let's say we want to derive y equals 2x squared plus 3 over x plus 1. So I said something like this before, you could, if it was something like over x, you don't need the quotient rule for this, although you could use the quotient rule for this. If it was something like this, you just, simplify it and then derive it separately. Right? So if it was something simple like that, you could just simplify it. So no, yes, we could use that product rule for that. In fact, you know what, for our demonstration purposes, this is the way on the right is the way I would do it. But let's show you, starting with an easy question where you don't need the product rule, how that would give us that answer. So we're expecting the answer to be 2 minus 3 over x squared. If we use the product rule, then we will say that you'll be putting it on 1 over x all squared. And then you will derive the numerator. And then you'll multiply by the denominator unchanged. And then you'll minus the derivative of the denominator, which is x, times the numerator unchanged, which is 2x squared plus 3. So take a look at that. Let me know if you have any trouble with the working there in terms of what's required. Everyone happy with what we're doing here? Or is it a bit too confusing?
I think it makes sense.
Yeah. Janelle, Tiffany, does it make sense?
Yeah.
Tiffany?
Yeah, makes sense.
All right, so then we just then work each thing out. So what's the derivative of 2x squared plus 3, Tiffany?
It's 4x.
Yep, so that one's there's 4x times x minus the derivative of x, Janelle.
1.
Yeah.
Oh, wait. Yeah.
So that would then be 4x squared minus 2x squared minus 3 all over x squared. So that would be 2x squared minus 3. So that would be 2x squared minus 3 over x squared, which hopefully you can see is the same. Does it make sense?
Yes.
So you can see that the answer is the same. Obviously, you wouldn't use the quotient rule in this situation when you can do it in a more easier manner, but I'm just showing you that the answer does end up being the same. Let's use one where we would use the quotient rule, most likely. So if I've got something like y equals 2x plus 3 over x squared minus 4, something like this, yes, we would use the quotient rule. So if you like, you can write this as u, and you can write this as v, or you can just do it directly, kind of like the way I did here, if you prefer. Up to you. Many students prefer writing them out separately. So if you want to write them out separately, that would be u equals 2x plus 3, and then u dash would equal, Tiffany?
U dash would equal 2x.
U is 2x plus 3, so what's u dash?
Oh, sorry. U dash would just be Yes.
Will it just be what?
2.
Okay, yeah, sorry. If you said it, I didn't hear it the first few times.
Sorry.
All right, it's maybe my internet was unstable or something. All right, and Janelle, what's the B dash?
2x.
Correct. And then you just sub everything in. Pay special attention to the order. Derivative of the numerator goes first. All right. So that means you've got 2 times x squared minus 4. And it's a minus, not a plus. Derivative of the denominator, 2x times the numerator. All over. And don't forget, it's denominator squared. Right? And then you can just do your and you're done. All right. So just to give you examples to work on, can you try and work out quickly using the quotient rule, or actually not necessarily the quotient rule. I'll give you a few examples on the quotient rule right now. But yeah, can you just give these 3 questions a go?
Oops, sorry. How you guys going with it?
I'm still doing the first question.
Still in the first question? Okay. So just for reference, I'll write it on the board for the moment. So if y equals u over v, then y dash must equal u dash v minus u dash. Almost done?
I finished the first one.
Oh, okay. Janelle, Tiffany, how you guys all finished the first one?
Yeah. First
All
one.
right. How about let's go through the first one to make sure you're all on the right track. So do you guys want me to write out the U and V separately? Would that help? Or just do it direct? What would suit you guys better?
Just do it.
Just do it? All right, so y dash, oops. So y dash would be derive the numerator, which is 6x, multiplied by the denominator. Remember it's minus, derive the denominator, which is 1, times 3x squared plus 4. And then you'll get x plus 2 squared. And then basically just do a bit of expansion. So that's going to be 6x squared plus 12x minus 3x squared, which is 3x squared. You're going to get 12x plus 4. So minus plus 12x minus 4 over x plus 2 squared. Is that what everyone got?
Yes. Yes.
Yep. Good. Any questions with that?
Nope.
All right. So that's how you do it. Can you guys quickly do the second one and the third one? Did everyone get the second one?
Yes.
Yeah. Yes.
All right. Now the third one obviously looks a little bit tougher, so just give that one a go. But it's the same steps, just maybe slightly tougher.
Sorry, I didn't realize I wasn't on mute. I'll mute myself.
Okay, when you think you've done the third one, you know, as best as you can, or let me know.
Yeah, I've done it, but I think I gave up expanding it.
Yeah, okay. To be honest, you know, you might need to do that sort of simplification, which I'll show you in a moment. So just kind of, I'm giving you harder ones to kind of test your algebra skills. So you might need to do that. Obviously, the key focus right now is to make sure you know, get the first line right? Apply the quotient rule. However, you know, as questions come up, you know, you're going to have to rely on your algebra skills. And obviously, sometimes people know the quotient rule full well, but they can't do the algebra, which is why I'm not limiting to just really, really simple ones. I'm throwing in, you know, fractional indices as well, and so forth. But just make sure that if you are having trouble with the algebra, that you work on it, because it's all very nice to say, yes, I understand the quotient rule, and that is the focus for today. But note that questions will get harder, and they will rely on you knowing your algebra. So if you struggle with that, you do need to work on it. Tiffany, Paris, how are you guys going with it?
I'm expanding it right now.
Okay.
Same.
So in that case, just make sure you guys have all the same right steps. So deriving the numerator, so 3/2, x to the minus a half plus 2x, multiplied by, I'll just start further down. Oops. So it'll be 3 times a half, x to the minus a half plus 2x, multiplied by 2x minus 4, minus 0 of the denominator, which is 2, and then 3 root x plus x squared, all over 2x minus 4 all squared. Well, what I might do is I might just multiply the 2 here in there, right? And so what that will simply do is that will change it to 3x to the negative a half plus 4x times x minus 2. And then there's not much you can do with the thing on the right hand side. That's minus 6 root x plus x squared all over 2x minus 4 all squared. And then there's probably not too much point in expanding this out actually. But since you guys are doing that, let's just quickly do it. So we've got 3 root x minus 6 root.
Minus 6 root x plus x squared.
Oh, plus. How did I get plus x squared there? Should be minus 2, it looks like.
I got plus.
I got minus 2x squared.
I got plus 2x squared too.
Well, it's the derivative of the first, multiply the second unchanged, minus 0 of the second, which is 2, times that unchanged, right? And so it's minus 2 times that, which is minus 6 root x, and then minus 2 times that, which is minus 2x squared here. Now, of course, we haven't expanded this yet. Once we expand this, you're going to get plus 4x squared, so it'll be plus 2x squared in the end. But, you know, this is this step here. Does it make sense? So let's expand it out. You're going to get 3 root x for the first one, then minus 6x to the negative a half, then plus 4x squared, minus 8x, minus 6 root x, minus 2x squared, all over 2x squared minus 4 all squared. And that will then be equal to 3 root x minus 6 root x is negative 3 root x plus 4x squared minus 2x squared is plus 2x squared minus 8x and then minus 6 all on root x. And if you want to make it look a little bit nicer, just multiply everything by root x. So numerator and denominator. So the denominator so your denominator will have a root x, 2x squared minus 4, 2x minus 4 squared. Then multiply everything in the numerator by root x. And then you'll have something like that.
Wow, that is not what I got.
Well, you might have something that's correct, but just in a different form, depending on what you've got. But look, I mean, the key focus is the quotient rule. So I guess from here, getting to here is really the key focus. From there, it's a question of how you do the algebra. You might have got something that's equivalent, but I've just made it look like this instead. Does that make sense?
Yep. Thank you for your encouragement and positivity, sir.
Any questions with that one?
No.
All right. So I'll just leave you guys to do these ones for homework, but I'll just give you guys examples. I mean, I've given you these examples before, but you know, so something like this, if you just think earlier in the lesson, what rule would you need to use for this?
Product rule
Is that all?
and chain rule.
So firstly, you would use the product rule because ultimately it's a product. And then within the product rule, you would need to use the chain rule, right? Just want to make sure that you guys can kind of see these, right? All right, what rule would you use?
Quotient
Is that all?
and product.
Right, you can see that the overall thing is a quotient, but that of course means you'll need to derive the numerator and the denominator. And in this case, the numerator will be a product rule. So you need to use the product rule as well for the numerator, right? All right. Tiffany, what rule would we need to use for this?
The chain rule and the quotient rule.
In what order?
The quotient and then the chain.
Right, it's ultimately a quotient, but when we do the numerator, we need to use the chain rule. All right, what if I did something like this? Paris, what would we need to do?
Quotient.
Is that all?
Need to do the chain rule
For where?
for the top part. Wait, yeah, for the bottom one, the denominator.
Is that all?
And then you need to do the product rule for the top.
Right. And you know, I could give you a question like this. So, you know, just running through it, you would need to start with the quotient rule. which means you will need to do the numerator and the denominator. For the denominator, you would need to use the chain rule. For the numerator, you would need to use the product rule. But the product rule is split into two of them, right? The 3x plus 4 power 7 and the 9x cubed minus 5 power 4, both of which would need the chain rule. Does it all make sense?
Yes, sir.
That's what I mean by, you just think of the fact that, you know, whenever you're differentiating at any time, are you differentiating a function times a function? That means product rule. Are you differentiating a function divided by a function? That means quotient rule. Doesn't matter if it's like halfway down, right? Doesn't matter if it's halfway down the steps. Are you differentiating a function of a function like this? 3x plus 4 is 3x squared plus 4, all to the power 7. That's a function of a function, or can be thought of as one. Then use the chain rule. Good. All right. So if you are confident with all those rules, then congratulations. Those are the rules for differentiation. And apart from learning more sort of specific rules for specific functions, like derivative of x, like the only thing left is to, you know, introduce different functions. So we've been sticking with this, and we've been then kind of been teaching how to do differentiation in general with just this function. It's a bit like we're teaching how to drive with a particular car. And you're done. You know how to drive. We'll be, as we progress, we'll be giving you different cars to drive. So things like e to the x, derivative of log x is 1 over x, and so on. Sine, cos, tan, right? But the chain rule, product rule, quotient rule applies for all differentiation, includes all the things there. So it's a bit like, you know how to car drives, you know how to accelerate, you know how to brake, you know how to, you know, indicate left, indicate right, you know how to turn the steering wheel, that kind of thing. The specific controls for that car for the same action might change slightly. Maybe this car has electronic windows, the other car doesn't, or things like that. But you get the gist. And in terms of the concepts behind it, that's how you differentiate. Does that make sense?
Yeah.
Good. All right. So we won't go through the other functions just yet. I'll let you get used to that. But now we'll talk about how to apply derivatives. So we want to use these to solve questions. Now, this helps to kind of go with this. You want to think of what dy dx represents. And what did we say dy dx represents? What does the derivative represent?
The rate of change.
Of what?
X.
Not the rate of change of x. Definitely not the rate of change of x.
Of y.
Yeah, it's the rate of change of y
For x.
as x changes.
Right.
Now, this is not new. We've definitely talked about it before. It was part of our review right at the start. dy dx represents a rate of change. If you want to be more specific, it's an instantaneous rate of change. Rate of change of what? Of y. Well, how does y change? As you change x, as you make small changes in x. Right? And so that's something we've been kind of drilling in from the start, but obviously we'll be focusing on that now. So the dy dx is an instantaneous rate of change of y as x changes.
I don't understand what you mean by instantaneous.
All right, so it's good that you want to, we should clarify that. So basically, it's a bit like, it's a bit like, before I draw a graph, it's a bit like, you know, how do you get to school, Tiffany?
By bus.
Right, your bus, all right? So when you're traveling on the bus, just give me a rough estimate. I don't care about the exact numbers. How long does it take the bus to get there? 5 minutes, 10 minutes? Like, just give me a number.
Sorry, I said something. 30
Oh.
minutes.
All right, it takes 30 minutes. How long is the trip, as in distance-wise?
Let's say 5 kilometers.
All right, so let's say, wow, okay, that's a really slow bus. Anyway, 5 kilometers in 30 minutes. All right, so let's just say, let's convert it to kilometers per hour. That's 10 kilometers per hour, right? Overall.
Yeah.
Right, as I said, pretty slow bus, but you know, peak hour, lots of stops and so on, maybe. All right, doesn't matter. Numbers aren't important here. The point is, you understand that the bus took 30 minutes to cover 5 kilometers, so it's 10 kilometers per hour. We all agree on that?
Right.
All right. So this is your speed, your sort of speed of the bus, right? It's a speed of the bus.
Is it that thing where you shrink like the number of?
It is. But let's kind of try and tie it into, you know, less about the definition and more about how you think about it. Now this bus, did it travel at 10 kilometers per hour the whole time?
Probably not.
Most likely not. Like in real life, it most likely had a traffic light and stopped, right? And then it sped up a bit more, and then, you know, it can't, right? It's got to start and stop to pick up passengers. So it didn't travel at 10 kilometers per hour the whole time. So if we're saying 10 kilometers per hour is the speed of the bus, what speed of the bus is it then?
Overall?
It is the overall, but let's pick a better word, a more mathematical word.
Average?
To describe. Yeah, it's the average speed of the bus over the trip. Right? Which, you know, in year 4, we treat as total distance divided by total time, which is exactly what it is. Does that make sense? But the note, importantly, the bus's speed changed during this time. Sometimes it stopped, sometimes it's going fast, and so on, right? So if I want to know what it's going at right now, and you're a passenger on the bus, what are you looking at, basically? If you want to know how quickly the bus is going kind of now.
You look at the graph? I don't know.
Well, you kind of, you know, go up to the driver's seat and look at the speedometer, right?
Oh, right, yeah.
So basically the speedometer essentially is giving you the speed sort of now, right? It's not, you know, it's not taking the whole trip and then dividing. It's kind of giving a speed now. That's what I mean by instantaneous. That's analogous to the instantaneous speed.
Right.
So assuming your thing changes, right? If you get something that never changes, well, then the instantaneous speed will be exactly the same as the average speed, because, you know, your bus goes at 10 kilometers per hour the whole time, no traffic lights, no traffic, nothing, right? Then instantaneous and average will be exactly the same. However, if it changes, then instantaneous essentially just means the one right now.
Okay.
Which could...
I just forgot, yeah.
Which could, but doesn't necessarily have to be, but it could be different to the average. Because for all you know, the bus could be going at 10 kilometers per hour right now as well. Right? So we're not saying it's necessarily different to the average, but the concept is different, right? One's the thing right now, one's the overall. Now, what does Y change as X change? What's that about? What's the rate of change of Y as X changes? What does that represent?
The gradient?
Exactly. So this represents graphically, this is the gradient. So because, let me do it on a new one. Because dy dx represents the gradient, now, in general, it's the gradient, but it's the instantaneous, right? It's the instantaneous rate of change of y. So it will be the gradient of what?
A point?
Well, you kind of have a gradient of a point. I mean, you might be on the right track, but the way you're expressing it is not correct. You can't, a point doesn't have a gradient, right?
A tangent?
Yeah, the tangent at a point, right? So if we've got the point P and we've got the point Q, then something like, you know, the yellow line, something like that. I know what I'll do. I'll cheat. So let's call it, that's P, and that's Q. So the gradient of PQ is just, you know, the y coordinate of, you know, Q minus the y coordinate of P divided by the x coordinate of Q minus the x coordinate of P, which is the average sort of gradient, you know, of the chord over P to Q. So that's an average gradient. That's a gradient of a chord. But if I'm interested in the gradient of the tangent, looking something like that, close enough, then this gradient of the tangent, sometimes called the gradient of the curve, would be represented by dy dx. And that's the key idea here. In other words, if we are thinking about things graphically, dy dx represents the instantaneous rate of change of y as x changes. It always does that. But as a graph, that means it represents the gradient of the tangent. Does that make sense?
Yes.
Good. All right. So then we will now start using this and applying this to the functions.
Joel,
Yes.
I have to leave now.
Yeah, sure, no problem. I will send you the link afterwards so you can take a look at it.
Yeah, thank you.
All right, you're welcome. See you. Bye.
Bye, Paris.
Bye.
So this is the gradient of the This is the gradient of the tangent. So let us take an example. Now let's start with something quite simple, like y equals x squared, which you know looks more or less like this. And you also know that it's got some point. Let's say it's got some point 24. And since it's got some point 24, we know that it will also have some sort of gradient. It will have some sort of tangent like this. So this would be the tangent to y equals x squared at P 24. So I'm going to label that point P. All right, everyone happy with that so far?
Yeah.
All right, so what we're basically going to do is, let's figure out what is the gradient of the tangent at P. Well, the first thing we need to understand is our curve is y equals x squared. Now, Tiffany, what's the derivative of x squared?
Sorry, I had to open the door.
All right.
Could
Well,
you
the question is, what's the derivative of x squared?
2x?
Now, importantly, what does this represent, being the derivative?
You see, I missed a lesson.
So this represents the, well, you do have the link, by the way, Tiffany, to catch up. But this represents the gradient of the tangent to the curve. So 2x is representing the gradient to the tangent. So they've got x squared. That means 2x represents the gradient of the tangent. So importantly, that means once you know what x is, then you can work out the gradient of the tangent there. Now we're interested in the point P, right? Because we're interested in the point P, do we know the x coordinate of P?
Yes.
Yes, we do. The x coordinate is 2. So here, we now focus on P. So for P at 2, 4, the x coordinate equals 2. Does that make sense? So then we would sub x equals 2 into the derivative. In other words, and sometimes you write it like this. So this is kind of, think of it like an fx, right? You don't have to write this, but this is a notation for it. This is basically saying that I'm subbing 2 into y dash. So it's a bit like when, f of 2 is subbing in, 2 into f, like into x for the function f. This notation simply means I'm subbing 2 into x for y dash. So that literally means that's 2 times 2, which is 4.
Yeah. Okay. Cool.
Does everyone understand what I'm doing here right now?
Yeah.
So what this then represents, this is saying that at x equals 2 on y equals x squared, that is basically P 2, 4. So basically at P, right? At x equals 2, for the y dash, which is the derivative of the curve x squared. So for the curve x squared at x equals 2, which basically means right at this point, then this is the gradient of the tangent. To y equals x squared at P is 4. Does everyone understand the steps I've taken there?
Yes.
All right. So I'm going to give you a new point. I'm going to call this Q. And I'll just call it -3, 9. And it's going to obviously have its own tangent as well. Can you quickly replicate the steps, for Q? I mean, we'll do more with it. So leave some space for this. I'm going to leave some space for this, but I just want you to kind of do your own one. I'll do it on the next page, but I just want you to, I want you to try it by yourself. So imagine this is Q -3, 9. I'll leave this on the board so you can refer to it. When you're done, let me know. How are you guys going with it?
Is it just -6?
Yeah, it's just -6.
Oh, okay.
Janelle, are you fine with it as well?
Yeah, -6.
Yep. All right. So all that's really saying, but yeah, it's just -6. Like, look, this thing is not hard, right?
Yeah, but you gave us so much time, so we overthought it.
Oh, well, I was waiting for you guys to tell me that you guys were done.
Oh.
so, you know, it's just going to be, you know, I mean, the derivative we've already done, right? So you already know it's minus 2x, and you sub in -3 in this case. And so it's just going to be -3, all right? So what does that mean, though? What does the -6 mean?
The gradient of Q?
Correct. Well, not the gradient of Q, because Q is a point, and the point doesn't have gradient. But basically, importantly, you've recognized that at this point, you know the gradient of this is -6, all right? And if you were doing this, you know, basically, we would say that, you know, y equals x squared, y dash equals 2x, then y dash of -3 equals -6, all right? Therefore, the gradient of the tangent at Q is -6. Everyone happy with that?
Yeah.
Yeah.
Good. All right. So I'm going to leave this one here. But now, that's the first step, right? We've worked out this gradient. So at this point, we know that the gradient of this point is, in my question, this one is 4. Now, what about if I want to work out the equation of this line? How do I work out the equation of the blue line?
Wait, sorry, could you repeat that? I didn't hear.
How do we work out the equation of this tangent, the blue line? We now have the gradient of the tangent.
Mm-hmm.
How do we work out the equation, though, if I want to do that next step?
You substitute the points.
Yeah, essentially. So if you know what you're doing, this is pretty simple. But can you elaborate what you mean by that?
Do you first put it as like y equals mx plus b?
Also, there's 2 ways to do it. So basically, what the important thing is, so let me just write out what we're trying to work out here. Essentially, what is the equation of the tangent? And more specifically, you know, 2y equals x squared at p 2, 4. That's really the question we're trying to deal with here. And you can refer to the earlier diagram. But the key thing that hopefully you recognize at this point is we already know at this point that the gradient is 4, and then it passes the point P to 4, right? We know the gradient, but we know it passes the point. So really, this is just your, you know, year 8 stuff now, right? Because a tangent is basically a line. And if you know the gradient of the line and a point it passes through, you should be able to get the equation. Now, Janelle has suggested that we use y equals mx plus b, given that we know m and 2, 4. That's not a problem. So let's do that first, all right? So we could sub 2, 4, and m equals 4, and I guess you work out b. So that means you will have 4 equals 4 times 2 plus b, so equals 8 plus b, so b must equal -4. Therefore, y must equal 4x minus 4, all right?
Yeah.
I assume that's what you meant, Janelle?
Yeah.
Yeah, no problems with that. All right. Tiffany, does that all make sense to you?
Perfect sense.
Do you guys know any other way of finding an equation of a line? Maybe you think like the way on the left better, and I have no problem with that. I just want to make sure you guys know kind of, you know, do you know any other way? You have a gradient and you have a point, and you want to find the equation of a line that satisfies those. Do you guys know any other way?
Probably.
So there's what's called a point gradient formula, where you go y minus y1
Yeah.
x minus x1. If you prefer the one on the left, I don't mind. It doesn't really matter. The ultimate end result will be the same, and you know the goal, you know, the information you start with is the same. The end result will be the same. You just sub in, of course, you know, 2, 4, where this is x1 and this is y1, and you sub in, of course, m is 4, and you know that just means I'm going to get y minus 4 equals 4, x minus 2, a bit of expansion, and you're done. You'll get the same answer. Does that make sense?
Yeah.
All right. Are you all happy with that?
Yeah.
Yeah.
All right. So at this point, we have now done what you did not know how to do before, right? We can now find out the equation. We not only work out the gradient of this line, being the tangent, which was a curve, rather than a straight line. We can now get the gradient. We can also get, you know, the fact that this is 4x minus 4. And so let's say I want to go further. Can I work out what the y-intercept is?
Yeah.
How do I work out the y-intercept?
When x equals 0.
Right, and so what would it be?
-4.
Yeah, exactly. And what would the x-intercept be?
When y equals 0.
So what would that be?
1.
1.
Yeah, exactly. So in other words, we have now, you know, I'm just redrawing it. So we can now definitively say, without question, that if you've got, you know, some so imagining that things are to scale and so on, if this is P24, then we know that that's 1 and that's -4. And this is the line y equals 4x minus 4, which is tangent to the curve y equals x squared at P24. Does that make sense?
Yep.
Good. All right. So I want you to do the exact same thing. So finish off the steps, but for -3. So, you know, work out the equation of the line, work out the intercepts, and then we will complete this picture. And tell me when you're done. How are you guys going with it?
Yeah, done.
All right, so we know the gradient, we know the point. So basically you'll get y minus y1 equals m, x minus x1, so x plus 3. So y must equal -6x minus 9. So given that, we know it's going to have a y-intercept of -9. And we also know it's going to have that of -1.5. Did you all get the same answers?
Yeah.
Happy with everything?
Mm-hmm.
Yeah.
Good. All right. So let me just quickly do one more example, just to make sure, you know. So let's quickly run through another example. So let's say x cubed minus 1. So you probably know x cubed looks kind of like, you know, like this. So because it's -1, it's now going to look sort of like that. That's the -1 there, and that's 1. So we've got something that looks like that. And let's say I'm interested in the point 2. 7. And let's say I want to work out all the kind of, so it's not perfectly drawn, but you get the idea. Should I redraw?
No, it's fine.
Okay. Yeah, it's not as clean as, yeah, it shouldn't, anyway, it should just curve up more.
Do you have OCD, sir?
No, well, it just doesn't, it doesn't demonstrate the point as nicely, I guess. All right. So you guys know what's, obviously this time the numbers might not work out so nicely. Clearly, common sense will tell you that this x-intercept won't be a whole number because 1 is here and 2 is here, right? So can you just quickly, I'll just run through it with you, all right? So I've got y equals x cubed minus 1. So what's y dash?
3x squared.
Correct. Now, we're interested in at what point?
2, 7.
Yep, so sub x equals 2. So y dash at 2 would equal?
It's 12.
Good. And what does that mean then? For our purposes, what does that mean?
M equals 12.
Correct. That's what it means. And since we know m and we know, that, then we can get the equation. You guys mentioned mx plus b, so let's use that this time just to make sure you guys know both ways. So if I use y equals mx plus b, subbing in, of course, 2, 7, and m equals 12, then basic times 7 equals 12x plus 2. Oops, not 12x, 12 times 2 plus b. So b must equal 7 minus 24, which is negative 17. So we now know it's 12x minus 17, which of course lets us know that somewhere further down is negative 17 down here. And then if we let y equal 0, then we'll get 17 over 12, which is between 1 and 2, which kind of makes sense.
Yeah, makes sense.
And so that, if you can, always give a sort of sense of what's going on as well. Like this is 1, there's 2, the line kind of goes like this, so we expect it to be 1 and 2, and it does, right? Don't do what lots of students do, which is, they just do it blindly. I mean, try not to just do it blindly. Obviously, if you do it blindly, but everything is correct, you'll still get the right answers. But a lot of students are supposed to do it blindly. They get something wrong, and they get some ridiculous answer like, okay, negative 54, for example, or like 100, right? They'll just go, well, my calculator told me that. Have a think about it, right? If the graph looks like this, the tangent kind of goes like that. 1 is here, 2 is here. So before we do any calculus, we know that this answer has to be between 1 and 2. And if you've got an answer for whatever reason that's not between 1 and 2, then you really should be setting off alarm bells and going and check.
Yes.
Does that make sense?
Yep.
Good. All right, so we talked about tangents. Now, the other thing we kind of need to talk about is normals. Do you know what, guys, know what a normal is?
A line?
Can you be more specific about what that line is?
A line with a constant gradient.
Well, all lines have constant gradients.
Oh, well, never mind. I have no idea.
Oh, you guys don't know what a normal is?
Didn't we learn this in class?
Oh, did we?
It was like the line that's perpendicular to
With
the
what?
green line, the tangent.
Right. So if you don't know this and you need to, so in maths and physics for that matter, the word normal, in this case, in this context, right, is basically a line perpendicular to the tangent. So we don't mean normal as in like normal, abnormal, like, usual or not. That's not what we mean at all. The word normal refers to a line that is perpendicular to the tangent.
Math and English don't get along.
Well, it's just the fact that a word can have more than one definition, right? Like the word right could mean, you know, the opposite of left. It could also
Okay,
be
I'm sorry.
wrong, right?
Right.
All right, so if this is our tangent, so this is our tangent at P. So this is the tangent to y equals x cubed minus 1 at P. But then graphically, that means this line here, approximately, not very good approximation, slightly better approximation. So this would be the normal to y equals x cubed minus 1 at P, where of course the understanding is that that's a 90-degree angle there. To the line. Does that make sense?
Yep.
Now, how do I find the equation of a normal?
How do you find the equation? Question. Janelle?
Well, how do we find the equation of a tangent?
You just use the slope.
Yeah, we found the gradient, and
Yeah.
we know a point, and we, you know, either way, it doesn't matter. We use the two information there together to get the equation, right?
Yeah.
Now the normal is still a line, right? So if we know the gradient and the point, then we can still do the same thing, right? Do we have a point?
Yes.
Do we have the norm? Do we have the gradient?
Yes.
How do we get the gradient for the normal?
You use the negative reciprocal.
Exactly.
Yeah, that's what it's called.
So if you guys don't know, and if you do, well, great. In general, if, you know, line 1 with gradient equals m1, and line 2 with gradient equals m2 are perpendicular, then m1 times m2 equals -1, or alternatively, m2 equals -1 over m1. Same thing. So we will use this, you know, knowledge that you've got from previous years to good effect here. So let us do it with a simpler question with nicer numbers, presumably. So the normal looks roughly something like this. Okay? The normal would be some, so we're expecting some answer that kind of sort of looks like this. All right. Of course, the key thing being that this is a right angle there. So not really much has changed, right? We just basically do the same steps. Of course, assuming I'm doing it from scratch, right? Because sometimes they just ask you the normal straight out. You take y equals x squared, you derive it as before, and then you still need to sub in at P. But remember, this is for the tangent. So therefore, for the normal, the gradient must equal -1/4. Do you guys see how I get that?
Yeah.
All right, once we've got that, then the rest of the steps are really the same, right? So now we've got the gradient equals -1/4, and we've got the fact that P goes through 2, 4. So therefore, you just pick whatever you like. I'll just use y minus y1. Or is it showing up? I guess it showed up. All right, so that means then, you know, just multiply, let's say, everything by 4. And so you could get something like, I'll do it in y equals mx plus b form, probably easier. Right? So y minus 4 equals -x/4 plus 1/2. So y must equal negative a quarter x plus 9 over 2, which you can then, work out that that means that this is going to be 9 over 2. Oops. And then you can sub in y equals 0. So that's negative 9 over 2 times 4. So that's going to be 18. Okay. Does that look right? Do the numbers look okay?
Yeah.
Yeah. And that's how you do it.
Great.
Does it all make sense?
Yeah.
Yes.
Good. All right. So this is important. Make sure you get this really well. So make sure you understand, chain rule, product rule, quotient rule, all of them really well. And then make sure that you understand how you go from them to apply to graphs. So derivatives in general to graphs. In particular, right now, we're focusing on tangent and normal equations. So your homework will then be to finish off, I believe it was chapter 11, but also to do 16a. So the way, your course does it now is a little bit, like the content's the same, but the way it's split up is slightly different. So we won't be finishing off the rest of chapter 11 right now. Oops, not 11. Which one was it?
15.
15. So if you haven't done it already, you should make sure that you know 15 A to D, all of it. Most of it was already done for homework. D is really the only one that should be new for you. And then, do all of chapter 16. Okay.
Okay.
Any questions?
None at all.
Good. Then let's leave that there for today. See how you go with the homework. Let me know next week, and I shall see you all next week.
All right. Thank you.
You.
All right. See you. Bye.